Well, all right, guys. So today we're on to 8.3, conservative vector fields. I already talked a little bit about these last time. In fact, most of this section is stuff we already know. So this is kind of going to be review. Almost everything in here is going to be review, except we can apply Stokes' theorem to get one additional conclusion, which is going to be summarized in Theorem 7, which are 4 equivalent notions of what it means to be a conservative vector field. So how about vector field F be a C1 vector field? On R3, except I want it to be C1, except actually I'll allow it to not be C1 at a finite number of points. Okay, then the following are equivalent. So let's see, we have that if you integrate f around any closed curve, you get 0. Or how about this one? If you have 2 paths that start and end at the same place, then it doesn't matter how you get from A to B. The path does not matter. If C1 and C2 are simple oriented paths with the same endpoints, then the line integral of f over C1 is the same as the line integral of f over C2. This is exactly the statement of path independence. Okay? When we've talked about path independence before, this is exactly that property. Oh, and I used the word simple there. Someone sitting in the back third of the class, is someone in the back third of the class able to tell me what simple means? Yes, sir. For sorry, so it's, I didn't hear the end of that. What did you say? You do a horizontal, horizontal lines can intersect it more than once, vertical ones can too, or even many times. Simple, so you're thinking of regions. What about for paths? The word simple has a different meaning. Yang, what's simple for paths? It doesn't cross itself. Yeah. Yeah, so it does not intersect itself. It's not a very big deal as far as the theorem or the definition goes. I just wanted to mention that so like you weren't confused on what the meaning of the theorem was. Third statement is what I originally presented as the definition of conservative, which is that f is a gradient. It is defined where f is defined, where capital F is defined. And fourth, that the curl of f is 0. Any questions on the theorem? So the proof is kind of nice. I thought I would just show you some of the details of the sketch of the proof. A lot of it we've already done. So like, let's see. If I wanted to show that, well, in a proof to show that 4 different conditions are equivalent, I'll show that 1 implies condition 2, which implies condition 3, which implies condition 4, which implies condition 1. So any one of them will imply any of the other ones. So to show that condition 1 implies condition 2, suppose that I have 2 paths that start and end at the same place. Like, let's say there's path C1, and let's say there's path C2. Well, if I go along C1 in reverse, let me give that a name. So how about I call this path C1 minus, is C1 in reverse. Okay, so then C2, if you traverse path C2 followed by C1 in reverse, that's a closed loop, right? That's a closed path. That starts and ends at the same place. So by 1, which the first one, remember, was that its integral around any closed curve is 0. So 0 should be the line integral of f around C2 followed by C1 in reverse, which is the integral of f around C2 plus the integral of f around C1 minus is what I called it. But as we know, and as appeared as a midterm problem, what happens if you go, if you integrate a vector field along a path in reverse? Everyone should know this one now. If you integrate a path moving backward, that's the negative of what you would get if you integrated the path moving in the forward direction. So I'll get a minus C1 f dot ds. So the integral of f over C1 is the same as the line integral of f over C2. Cool. What about to show that property 2 implies property 3? Okay, so I want to show that given a function is path independent, that it must be a gradient. This one's kind of neat. This one is related to how do you figure out what the function little f is? So, let's see, how am I going to do this one? We know that we have the path independent property. We want to show the gradient property. Right? We're working to show that this property implies this property. Okay, so we're going to let C be a path from, say, the origin. You can really pick any point. I'll just pick the origin to some other given point x, y, z. In fact, I'm going to choose a specific path. So not just any path. I'm going to show you the path. Let C be the path from the origin to x, y, z shown below. So let me draw it here. Say if this is the x-axis, y, and z-axis, and let's say here's the point x, y, z. Now if I project it down into the x-axis, here's the path C. First travel along the x-axis to the point x. Then travel in a direction parallel to the y-axis to the point y, and then travel in a direction parallel to the z-axis up to the point in question, x, y, z. So that's the path we're going to integrate over. And we find that the integral of f over that path, which is C, is equal to, okay, so over the first part, well, in order to write what it equals, let me write the components of f first. So let's suppose that f has components f1, f2, f3. In that case, the integral over this path is, okay, over the first path goes from 0 to x, and that's f1 of t comma 0 dt. The second path is from 0 to y, and that's f2 of xt 0 dt. And the third component goes from 0 to z of f3 of x, y, t, dt. So you can verify this if you want, but here's the cool part. Go ahead and take the take the gradient of this function and by the fundamental theorem of calculus, you just get back to the vector field F, the vector field capital F. Right? So define this to be f of x, y, z. Then by the fundamental theorem of calculus, and you can check this, this is only a sketch, I'm just doing a sketch of the proof, check that indeed, if you take the gradient of this function, you get back to capital F. And it didn't matter where we started, because that just amounts to shifting little f by a constant, which disappears when you take the gradient. You can always add a constant to the to little f, and it's not going to affect what its gradient is. Okay, that showed that property, and let's see which other. Okay, the next two are pretty quick. So to show that 3 implies 4, well, that's easy. If f is a gradient, then why is del cross f 0? Anyone know why? What's the curl of a gradient? Yes, sir? Yes, the curl of any gradient is always 0 by the equality of mixed partials. So this was a property that we verified in section 4.4. Curl of a gradient is always 0. Kind of like divergence of a curl is always 0, too. These are two useful identities. Okay. And finally, to show that 4 implies 1, this is the only one that really uses anything new. Let's suppose we have some path C. Well, enclose it in, let's S be the surface, any surface really, that has boundary given by the path C. And then the integral of our vector field around that path, we get to use Stokes' theorem here. This is the integral over the surface of the curl, but we just said, right, the assumption of property 4 was that the curl of f is 0. So this is 0. Cool. All right. Any questions on that? It's kind of cute, right? I like the path canceling property one, where like path independence is equivalent to the integral around any closed loop is 0. Okay, so I already mentioned this definition before, but I'm just going to say it again. When little f satisfies that the gradient of little f is big F, we call little f a potential function. And often, like in physical applications, little f has units of energy, so it's often called the potential energy. Sometimes physicists might put a minus sign in front of it, depending. Mathematically, the minus sign is not particularly important. Okay, here's an example. So I gave you some function. I'm asking you to show it's conservative. No, I'm not asking whether it drives a pickup truck or you know, chewing tobacco or believes in the free market. I want to use our new theorem which gave us 4 different ways to check whether a function is conservative. And I think the easiest is just take the curl. All right, it's just straightforward calculation. So solution, the curl of this function okay. So you can work this out. It's like x squared minus x squared, 2xy minus 2xy, and 2xz minus 2xz. So it's just 0. Or what we also usually abbreviate as vector 0. Cool, okay. So our new theorem says that f is conservative. Oh, is it C1? Yes, it is definitely C1 everywhere. So f is conservative. How do we find its potential, though? What's your name? Justin. And yours? Lior. Justin and Lior. You guys remember? What's the example I ended class with last time? What was I trying to do with that? It was something that has come up earlier in the class, but you didn't often know how to do it. It was how to work back. So you know how to take derivatives. What if you already know what the derivative of something is and you're trying to find out what the original function is? If you know what the gradient of a function is, how do you find the function? So I did this example where I showed you like a method for doing that. I feel like since I already showed you that, I'm not going to show you the same technique again. You can review the notes for that example or look at it in the book. But I'm going to show you an alternate method, actually. So here's an alternate way. It's an alternative to the method I showed last time. Okay? We use the formula from the proof of the theorem. So I'm talking about this formula. Okay? In other words, we let f of x, y, z define, this is a definition, equal the integral from 0 to x of f1. Okay, here, so let me label these parts. Like this is f1, this is f2, and this is f3. So f1 is, well, it's f1 of t0, 0 dt, 0 to y, f2 of xt, 0 dt, and 0 to z of f3 of x, y, t dt is 0 to x. F1 of t0, 0 is 0, right? Because z is 0 and y is 0. Similarly, f2 of xt0 is 0. The only non-zero term is the last term. The last term is 0 to z x squared y dt, which is x squared y z plus c. Any questions? Okay, let's see. How about example 2? How would I show a function is not a gradient? How about someone on the left, my left, stage left side of the room? Yes? What was your name? Noah. Noah, yeah, all right, Noah, what's going on?
Maybe find that the curl is not 0.
Oh, okay, cool. All right, good idea. That's perfect. Find the curl is not 0. So curl is determinant I hat, j hat, k hat, partial x, partial y, partial z of x, y, x plus y equals 1 minus 0. Some other stuff, actually, we already know it's not 0. I don't even care what the rest of it is. It's not 0 because, well, I can already tell because the first component's not 0. Okay. Oh, the gravitational potential. So I think I'm not going to fully work out this example, but I want to point it out. The gravitational potential is one we've seen before. The gravitational force field is some constants and product of the mass divided by r cubed r. So if we wanted to show that, for example, that the gravitational field is conservative, we could try taking its curl. I'm not going to do that because it's kind of a lot of work. You can see it in the book. It's one of the examples in this section. So, like, if you try to take the curl of this function, you have to use some of these vector differential operator identities that we learned back, well, that we saw back in section 4.4, like the curl of a, what are the identities? I don't even remember. Okay, yeah, like the curl of a product between a scalar and a vector function, for example. You could use that identity in order to show that indeed you get 0 for the curl. But wait, can we still apply the theorem? What is there left to... This force field has a singularity at the origin. It blows up when r is equal to 0. And there was something in the theorem about being C1, but this function is not C1 at the origin. Can we still apply the new theorem to this field? Yeah, Mike? Or, wait, was it Mark? Mike? Mark. Yes, exactly. So if you read the theorem carefully, you can have discontinuities. You can have it not be C1 at a finite number of points, and the theorem still works. So this one is not C1 at exactly 1 point, the origin, but then according to the theorem, it should still work. So the theorem still holds. And you can then solve the problem using a homework problem that I gave you, so you'll see why it's important, or one reason. So in 4.4 number 38, you have to show that the divergence of the gradient of r to the n is, what is it? nr to the n minus 2 times r. Did you guys have to turn in that assignment yet? Oh, okay. Oh, all right, so this should all be familiar now. So then just if you let n equal -1, that basically gives you the solution here now, right? So you find that f is equal to, do we have a minus sign? gm m over r. Minus sign, I'm going to get a minus. Yeah, okay, is our potential, is the gravitational potential. Okay. About the planar case, theorem still holds in the plane, or more or less anyway, almost. It's just one slight subtle difference. So if F is a C1 vector field on the plane, so of the form f is some function of x and y I hat and some other function of x and y j hat, then we have the following. dq dx equals dp dy if and only if f is a gradient. Any questions on the corollary? So one distinction between the corollary and the three-dimensional theorem is we no longer have this thing about allowing f to be discontinuous at a finite number of points. Because, and this speaks to something interesting and very non-trivial in mathematics. You can find counterexamples of functions that are discontinuous at one point and for which the theorem fails. This has like profound implications for what would happen if we lived in a two-dimensional versus three-dimensional world. So here's an example. Okay, so here's what can like go wrong here. So let's look at the vector field. F is equal to negative y comma x over x squared plus y squared. In that case, if I want to integrate over the unit circle, which is parameterized by cos t sine t, then the integral of f over the unit circle turns into the integral of, okay, let's see, negative y is negative sine t, dx is negative sine t, x is cos t, dy is cos t, x squared plus y squared is cos squared plus sine squared. And this goes from 0 to 2 pi. And what do I get? I get 2 pi. Oh, okay. So it would seem this function could not possibly be a gradient because we integrated around a closed loop, right? We started right here, went around the circle, and ended up back at the same place, and we did not get 0. Well, what's going on here? There's something weird about this function. It's got a singularity at the origin, right? It blows up at the origin, and crucially, our path encircled the origin. So there's actually a quite interesting field of algebraic topology and algebraic topology and algebraic geometry and differential geometry, which is related to so-called genus and winding number and how many times you go around a singularity. It's definitely beyond the scope of this class here, but I'm just telling you, like, there's something interesting that's going on right here. Also very important in complex analysis. Because so f is not conservative because the integral around a closed loop was not 0. But here's sort of the cool part. Let's check what the curl of f is. So the curl of f is, scalar curl. I can just, we're asking about the scalar curl. So let's just, let me just compute, okay, let's see, what's dq dx is ddx of the x component, x over x squared plus y squared is low d high minus high d low, square the bottom, and away we go. Right? Okay, so that's low d high minus high d low, square the bottom. And this ends up being y squared minus x squared over x squared plus y squared squared. On the other hand, dp dy is d dy of negative y over x squared plus y squared, which is low d high minus high d low over the bottom squared. Hey, that's the same thing. So this is a counterexample to the theorem in the case that the function is not C1 everywhere. Right? Like, so that shows you why this example demonstrates why you need that assumption of C1. You can get interesting, unnatural, spooky behavior with theorems when they have singularities, particularly if the path encloses the singularity. Last thing I'm going to say is something about curls. So our theorem for gradients was if the curl is zero, if the curl is zero, then the function is a gradient. And we proved that by exploiting the fact that the curl of a gradient is zero. But there's another theorem about differential operators. What's another pair of operators that annihilate each other? So sure enough, yeah, the curl of a gradient is zero. What's the other one where divergence of a curl is also zero? Okay, but so similarly, since the divergence of a curl is zero, we get an analogous theorem. But it's a little bit harder to prove. So the theorem is that if vector field F is a C1 vector field on all of R3, with its divergence being zero, then there exists another C1 vector field that F is the curl of. This comes into play, what's it called? In gauge theory and electromagnetism. You try and find the vector potential. Yeah. So I don't know if any of you have learned much E&M yet, but you use exactly this theorem to derive the existence of a so-called vector potential. So this vector field G satisfies that F is the curl of G. Cool. Oh. Man, I covered a lot today. I just didn't ask enough questions. All right. Well, yeah, that's all I got. So we can stop a little bit early.